Hello everybody, following this MFPS talk. My name is Christine Tasson, and I would like to thank the organizer of MFPS for organizing this conference, this online conference, and for the invitation. So today I will present a joint work with Martin Ireland, which is on the linear-nonlinear substitution monad. And if you are interested in knowing more on this work, you can have a look at our archive paper. We get interested in this subject by discussing on what is the model, what is the axiomatization of differential lambda calculus. So I will start by presenting this work that was introduced by Erhard and Renier. When they were looking at semantics of linear logic, they observed that in some models made of topological vector spaces and smooth functions, there is a differentiation operator. And if there is a differentiation operator in the semantics, there might be a differentiation operator in the syntax that behaves well. And the question is, what is its signification? What is its meaning? So the differential lambda calculus is an extension of the standard lambda calculus with a differentiation operator that is a kind of linear application. And that corresponds to the derivation in standard mathematics. If we have a look at reduction, beta reduction is for the usual abstraction. So for instance, if we have an abstraction applied to a term n, the beta reduction will replace every occurrence of x by n, and there is no more binding by x at the end of the reduction. Now, if we look at the differential application, the reduction is a little bit different because we will, the idea is to replace only exactly one occurrence of x in term m by n. Okay, so here, if I want to replace only one occurrence of x in m, I have to choose one and to replace it by n, and I keep the other occurrences of x and the binding of this variable. Because I can make different choices for substituting one variable, I have to add some additive structure to my calculus to be able to superpose the different choices, non-deterministically, the different choices of variables that I replace. So this has to be compared to the linear approximation of a nonlinear function. Now we were interested in understanding what is the axiomatization of the differential lambda calculus. And there are some categorical axiomatization. So we start from a model of lambda calculus, which is a Cartesian closed category. We add some additive structure to interpret this non-deterministic choice. And then we add a differential operator. The role of the differential operator is to take a morphism from A to B and to compute a new morphism from A cross A to B, which is mimicking the differential operator. But here you know that there is a variable x, which is nonlinear, and another one u, which is linear. And we have to ensure that it is the same for this differential operator, but we have no tool to say that this variable a, this type a, is linear. So one way to do that is to say that the differential operator applied to f commutes on the left-hand side with the additive structure. But I think that it is not necessary to use the additive structure to ensure linearity. So if we want to speak of linear variables and nonlinear variables, we can go back to linear logic, in which the idea is to annotate nonlinear types with a shriek. Then in linear logic, you have two kinds of types, the one that are annotated, which are nonlinear, and the one that are not annotated, which are linear. So now a differential categorical is a model of linear logic that is a symmetric monoidal closed category together with a coalgebra modality that gives rise to a co-commutative comonoid. And we have to ask for an additive structure for the interpreting the non-deterministic choice. And we have to add also a deriving transformation that will transform a morphism from A to B, that is understood in linear logic as a linear morphism from shriek A to B, into a morphism from linear A, tensor shriek A, that is nonlinear A, to B by precomposing by this derivation transformation. Okay, but the problem here is that when we add this shriek, it can appear everywhere because it is a comonad on our basic categories. So we could have morphism from bang A, tensor bang B, tensor bang C, tensor D to bang A. So here we are not able to recognize what are the linear variables and the non-linear ones because there are shriek at different places. And here, what is the meaning of non-linear variables at the result of a morphism? So to avoid this problem, we can use a different approach in which the shriek is hidden. And for this, we can use the term calculus for intuitionistic linear logic, which was introduced in the 20s, and in the 20th century. And here I use the dual intuitionistic linear logic presentation. That judgments are made of two different contexts, one for the linear types and one for the nonlinear types. And a term can have any type. So there are three types of rules. The first group of rules is standard for multiplicative linear logic. If we just get rid of delta, which stands for the nonlinear context, then we just have multiplicative linear logic. So what do these rules say? The first one is an axiom. If I have a linear variable, then I can just get a linear term typed by A. I have an abstraction that takes a linear variable here and transform it to an abstraction of type A linear B. And I have a linear application which will concatenate the contexts. Okay. Now, for the nonlinear group, if we get rid of gamma here of the linear part, sorry, then it is just simply typed Lambda-Calculus. Okay. And what does it say? It says that from a nonlinear type, I can deduce a linear type. And if I have a nonlinear variable, then I can just compute an abstraction. And I have the standard application. Notice that here there is this delta here and delta here are contracted. So this axiom here, because of the presence of delta, means that we have weakening, and this application here, because delta is contracting, means that we have contraction. Notice also that here I forced term to have no linear variable. It is to avoid repeating linear variables. And now I have a last rule, which is a linear nonlinear rule, and which says that if I know how to type a term t with a linear variable x, that means that t has only exactly one occurrence of x in it. Okay, so if I know how to type t with this linear variable, then I can feed it with a non-linear variable because x appears only once in t, and it's not a problem for non-linear variables to appear 0 times, once, or many times. So here we have a version of linear logic without the trick, and we want to inspire our axiomatization from this presentation. And to do that, we have to move from categorical axiomatization to multi-categorical axiomatization. So let's have a look at what is a categorical axiomatization. In a category X, which is equipped with the right structure, either symmetric monoidal closed category or Cartesian closed category, types are interpreted as objects and terms are interpreted as morphisms. But to have a morphism which takes into account the context, I have to turn the context, which is a sequence of type, into an object of the category. That is why I need to have a construction such that tensor product or Cartesian products. So in multiplicative linear logic, a proof or a term will be interpreted as a morphism from the tensor product of the types to C. And in Lambda-Calculus, it will be interpreted as a morphism from the Cartesian product to C. What we want to do is to replace this tensor product and Cartesian product with a multi-category which define the interpretation of terms as multimorphisms. So I don't have to turn this context into an object of my category. So in a multi-category, types are interpreted as objects in the category, and terms are interpreted as multimorphisms. And it is the structure of the multi-category which will tell me what is the structure of the context. So in a symmetric multi-category, I will interpret multiplicative linear logic proof, and in a Cartesian multi-category, I will interpret Lambda-Calculus term. But we can, in order to express how to describe the context, Cartesian context with weakening and contraction, or symmetric monoidal context with just the exchange, I have to describe multi-categories with a fancy presentation using distributors combined with a monad that describe the context. So to be able to describe these multi-categories, I have to introduce some constructions, which are distributors, classes, bicategory, and monads, and two monads. And I start from the well-known category of sets and relations, because the bicategory of distributors, which I call prof, is a generalization of a L. Indeed, a relation can be seen as a function from y cross x to 2 with the standard composition, and a profunctor is distributors from y up cross x to set. So I have replaced 2 by set, and the composition is a generalization where I replace the existential quantifier by this coend, and the wedge here by this Cartesian product. Okay, so now a relation can also be seen as a function from X to the subsets of Y. So it is living in the Kleisli category of the power set monad. What I'm saying there is that the rel category can be identified with the Kleisli category over the power set monad. Similarly, a distributor can be seen as regarded as a functor from X to a presheaf of Y, where presheaf is the presheaf pseudomonad of on cat. And the bicategory proof is can be seen as the Kleisli bicategory induced by this presheaf pseudomonad on cat. Okay, so now I need something. I need a tool to describe the context, and for that I use monad. So if I come back to the rel setting, I can see that the commutative monoid monad, which is generating finite multisets, extends from set to rel. It is a monad on set, and I can see it, extend it to rel, because there is a distributive law of the power set monad over the commutative monoid monad. Similarly, a two monad T on cat can be extended to prof if there is a pseudo distributive law of the presheaf pseudomonad over T. And that is what we are using for describing multi-categories with special two monads for describing the context. So we will use the two monad L, which is acting on cats and which takes a category and computes the free symmetric monoidal category, and the monad M, which is also two monad on cats and which generates the free category with product. Okay, so these two monads are describing the context for multiplicative linear logic and Lambda-Calculus. So a multi-category can be seen as a distributor in the Kleisli bicategory of the monad that we have extended to distributors. So we can see N as a distributor from X to Tx, that is a distributor from Tx up cross X to set. But we want to interpret axioms and composition. So we need to have a monadic structure on M, that is an identity, and a multi-composition. So now if I come back to the axiomatization with multi-category, but now presented with distributors, if I have this multi-category, types are now interpreted as objects in X, and terms are interpreted as elements of M, but taking into account the context. So let's have a look at the multiplicative linear logic interpretation. So I choose for the two monad, the substitution two monad L, which is generating the free symmetric monoidal category over X. And I interpret a term which is type in a linear context as a morphism, a multimorphism with this type. And in Lambda-Calculus, I choose M, which is generating the free category with product over X. And I interpret a term into my Cartesian multicategory, which is multimorphism taking into account the type, the nonlinear types of my term T. Okay, so now I know how to describe what is the axiomatization of multiplicative linear logic and of Lambda-Calculus. But what I really want is to have the interpretation of a mixed linear nonlinear calculus. So I need to describe what is the correct substitution to monad T for mixed linear nonlinear calculus, and what are the free categories that are generated, that that are the T algebras. So how can I interpret a term with a mixed linear context and non-linear context? So I know I have an idea of how to do that concretely, because I know how to describe concretely what are the objects of L of X. There are sequences, and morphisms are just bijections and sequence of morphisms. And I know also how to describe N of X, which is the free category with product over X, and the objects are sequences, okay? But the morphisms are different. They are made of functions and sequences of morphisms. Now I have an idea of what should be Q, which is the mixed linear nonlinear substitution monad. The objects are mixed sequences, just as the context we were looking at, and the morphisms combine functions, bijections, and sequences of morphisms. Okay, so the question now is how to construct Q from L and M. And for doing that, I need to introduce or to study Colax colimits on two categories. So what on earth is that? Imagine we have a map in a two category, which I call lambda, and I can consider the Colax colimit, which is a cocone of this type. So I have two maps to C, and I have this two cell alpha. This Colax colimit has two universal aspects, one for the one cells and one for the two cells. Let's have a look on the one cell aspect. The universal properties say that if I have another cocone, D, with the structure F, G, and the two cell phi over lambda, then I can factorize it through a morphism from C to D. And if I take alpha followed by this unique morphism, I get this cocone. Okay, and I have also two cell aspects, which say that if I have two cocones which are in correspondence, then I have a correspondence between the two induced map from C to D. Okay, now I have described this construction. I can apply it to the map lambda from L to M. Remember, L is the free symmetric monoidal two monads, and M is the free category with product two monads. And every category with product is a symmetric monoidal category, and I can just compute the free category with product on a symmetric monoidal category. That is why I have a map of monads between L and M. So I can construct these Colax colimits in the two category of symmetric monoidal category, because we want that our monad is a substitution monad for context has to be symmetric monoidal in particular. So let's have a look at this Colax colimits. So I have this map lambda from Lx to Mx, and I compute the colimit, which is Qx, together with K, L, and alpha. Let's have a look at the concrete description of all these ingredients. So we know that Qx is made of sequences with two kinds of variables, the linear ones on the left-hand side and the non-linear ones on the right-hand side. Lambda is taking a linear context, so a sequence of linear types, to a sequence of non-linear types living in Mx. K is taken linear types into a sequence of linear and non-linear types. So we will put the linear types on the left-hand side. L is taking non-linear types, and we put them into mixed linear, non-linear context by putting them on the right-hand side. Now we have these two cell alpha, so that there is typo here, it is a morphism. which takes a sequence in Q. Alpha is actually a morphism in QX, which takes sequence with only nonlinear types and produce a sequence with the same types, but by seeing them linearly. So this morphism corresponds to this rule, which can be deduced from the linear-nonlinear rule, and which say, well, if I know how to type T with exactly x1, xl, exactly one occurrence of x1 and xl, then I can type T with nonlinear variables, even if I use them exactly once. Okay, so now from this construction and using one cell universality and two cell universality, I can compute the properties of Q, of QX. So first of all, it is a symmetric monoidal category. Indeed, I have computed my colimit into the two categories of symmetric monoidal categories. So the result is a symmetric monoidal category. Secondly, it is nearly a Cartesian category. What do I mean by this is that I can split it through the free category with product. Sorry, here it should be with product. So what is F doing? It takes a linear nonlinear context. It puts everything in a nonlinear context, and then back to QX, every types have been made in the nonlinear side. Okay, so intuitively, F is taking mixed linear and nonlinear things, and it put shrinks everywhere behind it, because it looks at it at every types as a nonlinear one. And indeed, F is a comonad that is strictly monoidal and which is strictly idempotent. So that means that we have a cell which is really important, which is beta, and which is a morphism in QX from context with only nonlinear variables to a context with both linear variables and nonlinear variables. Again, it is an instance of the linear-nonlinear rule, which allows me to move linear variables into a nonlinear side of the context. Okay, so now what do I have? I have computed a mixed nonlinear context on each category X, and I have described the structure of QX. And from the universality of the colimit, I can prove that Q is a two-monad on cat. And moreover, I can describe what are the Q algebra, what are the Q algebra, what are the free, what are the Q algebra. So a Q algebra is a symmetric monoidal category with a nearly Cartesian structure, meaning that I can split through a Cartesian category, and I have some coherences, of course. So this theorem is a nice presentation of a more theoretical one, which appears in our paper, but which is needed if we want to prove smoothly that Q is a two-monad and that its Q algebra have this structure. Okay, so we are nearly done. Not really. Okay, what we want to do is to model linear-nonlinear calculus. So we are looking for a multi-category axiomatization. That means that we need a two-monad Q for describing the context. So what we have done is that we have defined a two-monad Q on cat, which describes the linear-nonlinear context. And we have described its Q algebra. But what we need to do now is to describe what is a Q multicategory. And to do that, we need to extend Q to a pseudomonad on the bicategory of distributors. So how can we do that? instead of extending directly Q to a pseudo-monad, which is quite hard, we use the equivalence presentation through distributive laws, pseudo-distributive laws, and it is equivalent to prove that the pseudo-monad of presheaves lifts to pseudo-Q algebras. But the problem is when we apply the presheaf pseudo-monad on L algebra, what we get is a pseudo-L algebra. So L algebra is symmetric strict monoidal category, and what we get is just symmetric monoidal category. And there is no way to have a colimit here, because in the universal property, we need to have a unique map. And it is not compatible with this weak setting. So how can we do that? So our idea is to start from our characterization of Q algebras and to deduce a pseudo version of the Q algebras to see what are pseudo Q algebras. And now we need to recover our faculty to compute colimits, because our proof is based on this universality and on the colimits. So if we want to use the proof techniques that we have developed, we need to have a way to go back to a strict world. And for that, we can do power replacements that amounts to strictify the pseudo algebras in a world where we can compute colimits. But it's ongoing work. And when we will have done that, we will be back to describe what is the axiomatization of first mixed linear nonlinear calculus. And for that, we'll need a closed structure that is made to interpret abstractions, and we will follow the work of Fiore, Plotkin, and Thury, and the description of Lambda-Calculus in modern dress. And so an orthogonal issue is the differential operator, because we don't really need the closed structure today to speak of differentiation. So if we want to speak of the differentiation, we need a derivation operator. So remember, in the differential linear logic, that is the categorical axiomatization, we have an derivation transformation that goes from A tensor trig A to linearly to trig A. And what we want to have is to include this derivation transformation into our Q multi-category context. So a nonlinear multimap of type gamma, nonlinear B to C, will have to be transformed by the derivation operator into linear nonlinear map with one occurrence of B which is linear and one occurrence of B which is nonlinear. And then the last ingredient would be to describe how this derivation operator acts with substitution. And this is the chain rule, which will induce an additive structure. But what we believe is that we have a more primitive description we will have a more primitive description of what happens. And a nice way to describe the linearity without referring the additive structure. So I want to say thank you to have listened to the end of this talk. And if you have questions or if you want to know more, you can either ask them on Slack or go to our archive paper. Thank you very much.